Okay, so hello everyone, welcome to all to this third lecture. Uh, so today we are basically going to talk about the curvature in metric spaces. Uh, there will be different notions of curvature. Basically, we are going to talk about non-positively curved spaces, and I will mention some different notions of non-positively curved spaces in the general metric space setting. The way we how we defined it, and how is it related to the Riemannian metric. Riemannian manifold with non-positive sectional curvature, and the proof of that fact will be more clear in the next extra session on the Riemannian manifold as a metric space. Okay, so okay, so let me start. Okay, so basically, the theory of non-positively curved spaces starts with the work of Hadamard, where he considered. Okay, so let me just. It is sorry. So basically, this goes back to the work of Hadamard in uh, 1898 around. So basically, Hadamard considered a surface. So you take a smoothly. Uh, I would recommend that if this like okay, let me. So if you take a smoothly embedded surface in R3 and with non-positive curvature. So Hadamard made a fundamental observation that the distance function from a fixed point to a point that moves along a geodesic in this surface is basically convex. Okay, so it means that if you take a, let us say, just if you take a surface and we take a point, and we take any 2 points and a geodesic joining these 2 points, then the distance between P and, let us say, this is gamma of T. So this distance P from gamma of T means that this is a function GT. This is basically is going to be convex. Okay, so this is a rough description of the observation made by the Hadamard. Why I'm mentioning this, because this is the basically the foundation of the notion of curvature in metric spaces. Okay, so basically,
Here, gamma is any geodesy.
gamma is geodesic joining 2 points x and y.
Okay.
Yeah, I will make this thing precise. Just I'm just giving a brief history of non-positively curved spaces. Okay, so and this is a surface S smoothly R3. So basically, this naturally comes with the Riemannian metric. If you want to see this one can refer to my previous lecture on the post-classical problem, the way we get the metric on S for a smoothly embedded surface in R3. So basically, once it is non-positively curved, this is the observation that the distance function is basically convex. And in 1948, Busemann introduced his notion of convexity. 1948, around 1948, and basically Busemann take this observation to define the notion of non-positively curved spaces for a general metric space. Okay, so that we call it as a geodesic metric space is said to be non-positively curved in the sense of this one. Okay, and again, this is I will I will mention this thing precisely later. This is depends upon the convexity of the distance function, Busemann convexity. Later on in 1957, this is Alexandro. So Alexandro basically introduced several equivalent definitions for a metric space to have curvature bounded above from K. Okay? So here K is any real number, and now these definitions are known as basically cat K conditions. So these conditions are known as cat K conditions. Okay, and then there was a notion of again all these things, Busemann convexity and Alexandro notion of cat K conditions. These are all related to the Riemannian manifold with sectional curvature. Okay, and then there was a notion of visibility by Abraham O'Neill, which is kind of a natural replacement of strict negative sectional curvature. Strict negative sectional curvature. By this we mean that the sectional curvature is less than or equals to K, where K is less than 0. Something like this. and then the notion of Gromov hyperbolicity comes in the picture, which was introduced by Gromov in around 1987. Okay, these are all the notions of negatively curved spaces. And in this section, so in this talk, we will be mostly focusing on Alexandro geometry, means the cat K conditions, and we will give it will be kind of a short introduction to the cat K spaces, and in the next lecture we will talk about Gromov hyperbolicity, and visibility we will talk about once we are going to talk about the notion of boundary at infinity. Okay, fine. So let's start with the definition of okay, so let x comma d be a geodesic metric space. And so I will define the comparison for distance function. So fix a point p belonging to x and define the function dp. Dp is defined, so basically dp is defined x to 0 infinity, and dp is defined by dp of x is nothing but the distance of x from. Okay. So what we're going to do is we are going to replicate the idea of Hadamard, the observation of Hadamard in this case of metric spaces. Okay, so what we're going to do is, so for a geodesic, remember that geodesics are always parameterized by R-plane. So for a geodesic curve, let us say from 0 to t to x, and this joins gamma of 0 equals to a and gamma of t is equals to b. We are going to define a function g of t, which is nothing but d of p comma gamma to t, okay, which is nothing but dp of gamma t. Okay, so this is basically we have 2 points A comma B, and we have a geodesic joining this one. P is somewhere here in the metric space, and we are just taking the distance between these 2 points, like distance between P and this at particular distance T, gamma of T. Okay, we are defining this function GT, and this is kind of known as one-dimensional distance function. What we want to do is we want to compare this distance function with an appropriate one-dimensional Euclidean distance function. Okay, so how we are going to do that one is like, so our aim is to kind of we want to compare G with an appropriate one-dimensional Euclidean distance function. Okay, so for this one, basically choose a segment segment of the same length as gamma. Okay, and take a reference point. So what we're going here, what we're doing is like so here we have 2 points A comma B in a metric space. We have a curve geodesic joining gamma joining A to B, and its length is obviously LD of gamma is basically T. Okay, so we are going to take a Euclidean line segment of this length T, and for a reference point for a reference point P, let us say P bar, such that, so we are going to choose a reference point P bar such that basically A bar to P bar. So basically, obviously, we are taking a segment in the Euclidean space. What we are doing is like take 2 points A bar and B bar, and here is our segment of the same length. Okay, and the reference point bar, how we are going to choose it, like so it will be like distance from, so this is a Euclidean distance. This is a Euclidean distance between A bar and P bar, and this is basically going to be dP of A, which is nothing but d of distance from A to P. So whatever the distance is here from A to P in this metric space XD, we are taking that distance, and we are taking P bar, so that this A bar to P bar Euclidean distance will be nothing but distance between A to P in the metric space X comma D, and and uh, and B bar to P bar is basically dP of D, which is nothing but d of uh, B comma P. Okay, so let me call this segment as gamma naught. Okay, this line segment as gamma naught. So now we can define Z naught T as nothing but Euclidean distance between this P bar and gamma naught. Okay, so remember that. Let me just write it down here. AB, and here is P. So this basically, let me say this is your D of A comma P. So this is basically equals to D of A bar comma P bar, and D of B bar comma P bar is basically equals to D of P comma B. Okay, is it clear? Okay, so our ideology is to replicate I mean, to use the observation of Hadamard. So how we are going to do is, so for non-positively curved spaces, what we are going to do is we want this G naught to be convex. What does it mean? It means that G naught of T is less than or equals to G of T. Okay, we want this condition, and this is going to be so this is going to be our definition. Uh, we say, so this we will define as locally, okay, not as globally. This definition we are going to define as locally. So we say that x comma d, we say x comma d is non-positively curved, if for every x belonging to x, there exists a neighborhood. There exists a neighborhood, let us say, and p depending, x such that whenever p and a segment, geodesic segment. So this is a geodesic in this metric space x comma d segment gamma lie within this neighborhood. The comparison function g naught for one-dimensional distance function. What is that one? This is a one-dimensional distance function, nothing but gt of d of p comma gamma t. This satisfies, so basically g naught satisfies g naught of t is less than or equals to g of t for every t basically belonging to 0 comma t. Okay, so this is our definition for x comma d to be non-positively curved. I will come to the definition, but before that, we will compare some different notions, different equivalent ways of defining it. Up to this, is it clear? So what we are doing is we are taking a geodesic joining 2 points A comma B in a metric space, and what we are doing is we are taking a reference point P, and we are taking the distance from distance between P to gamma of T. Means we are running the points on this curve only, okay? And we are taking the distance. We want to compare this distance with the Euclidean distance, and what would be that comparison? So we need to construct a segment which has the same side length. What does it mean? It means that the length of the curve gamma will be equals to the length of this segment gamma naught, and the reference point we will choose accordingly. What do we mean by accordingly? It means that the distance between A to P will be equal to distance between A bar to P bar, and the same for B bar to P bar. Okay, once we have this one, we can define the one-dimensional Euclidean comparison function G naught, and this G naught will be compared with G. Okay?
Hello.
Yes.
So this triangle A bar, P bar, A bar, B bar, and P bar is in the Euclidean space Rn, right?
A bar, B bar. Yeah, exactly. This is in Euclidean space.
Usual Euclidean metric.
Yeah.
And is there any choice about that n R2, R3, R4? or any n.
Sorry, what?
On a Euclidean space mean what? When R2 or R3 or Rn is any k. There is no deal with the metric space and that k n.
So for instance, you can take this in R2.
R2. Okay. Okay.
Yeah, it
Oh,
doesn't
oh,
matter. That
I
I
can
will
take
come
also in
later.
R.
Yes.
Okay. Okay. R2 or R3 doesn't matter.
Yeah, yeah.
That's
So at present, you just think it of as in
R2,
R2.
R2, R2.
Yeah.
Okay, okay. R2 is usual Euclidean
Yeah,
metric.
in the Euclidean distance. So we are basically comparing with this distance function with the Euclidean distance function.
Okay, okay,
Yeah. So
okay.
basically,
Thank
what
you.
we're trying to do is like if you see in the negatively curved spaces, let me just give the geometric intuition. The geodesic triangles looks like this. They are basically quite thin, and the Euclidean space they are something like okay. So what we are doing is we are comparing the distance function from in this Euclidean space and in this non-positively curved space, so that we want this thing to be in a particular sense. Let us say I will define in the later stage, which is known as the k-thin triangle. Okay, under this assumptions, like uh, 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 taking this definition into the picture, I will define when we say that the triangles are k-thin. So basically, it will be like distance between any 2 points u and v will be less than equals to distance between any 2 points u dash and v dash. Okay? So this is kind of known as a thinner version of Euclidean triangle. Is it fine?
Yeah.
Okay. Okay. Then, like I mean that will come later. That we'll discuss in detail. Okay. So this is a one such thing. I'm going to define this thing, this comparison of distance function in terms of triangle. So that will be kind of a word by word formulation of this thing, uh, and that will give us a definition of cat zero spaces. So this thing is nothing but the equivalent way of saying the previous one. So this is as a triangle condition. Okay, so let us say this A B C be a geodesic triangle in X. So by geodesic triangle, I mean that we have 3 points, and we are joining it by a geodesic triangle. Let's say something like this. Okay. So this is a geodesic triangle in the metric space X. Uh, we construct. Okay. By the way, the existence of the comparison triangle in the Euclidean space comes by the Alexandrov's lemma. Alexandrov's lemma that I'm not going to discuss here, but I will mention it as a reference. One can see that one. So once I'm going to define the kappa spaces, and once kappa is less than equals to 0, we always have this comparison triangle. So we construct a triangle with with the same length. Same length by I mean that geodesic joining A to C. So here will be the comparison. So comparison triangle is like in the Euclidean space, it is like A bar, B bar, and C bar. So this length is equals to this length is equals to this length, and this length is equals to this. Okay? That is what I mean by the same length. Same length sides. that is the length of a comma b is nothing but the length of a bar b bar. A length of b comma c is nothing but length of b bar c bar, and the length of a comma c is nothing but a bar c bar. Okay, so now what? So here's our definition. Another one. So this is like uh, equivalent to the previous definition. So X is non-positively curved, non-positively curved if in some neighborhood of each point, X belonging to this metric space X, the following holds. Okay, it means that for every geodesic triangle ABC, and every point basically D belongs to A comma C. In between this, if you take any point here somewhere in A and C, one has DB is equals to, is less than or equals to, so distance between DB and this is less than or equals to distance between D bar and B bar, where D bar is the point on the side on the side on the side A bar C bar of comparison triangle. Comparison triangle C bar, such that the length D bar and B bar is nothing but D and D. Okay. Oh, wait a minute. Sorry. So this is our let us say any point on this one D, and we will take this image on this one, and this will be your D bar, and this we are going to define it as so basically here we have a comparison map between these two triangles T and just a T bar, F from T dash to T bar, which F sends A to A bar, F sends B to B bar, and F sends C to C bar. and and basically F restricted to each of these sides are nothing but the isometry. So this is kind of a map, and we have F of D is equals to D bar. This map F of a map of so image of D under the map F is nothing but the D bar. Okay, and we say that X is non-positively curved if in if you take any point in X, and then there is a neighborhood such that the following holds. Every geodesic triangle in that neighborhood, and for every point D belonging to the sides A and C, side joining A and C, one has this inequality. It means that the length of D to B is nothing but I mean, this length of D to B, whatever it is, I mean, in the metric space is nothing but D bar to B bar. This will be this. This will be less than or equals to this one. Oh, sorry, this will be the Euclidean line segment, and this will be some curve joining D to B. So basically, in the metric space D, so D of basically this point D and B is nothing but D bar to B bar. Sorry, less than equals to D bar to B bar, which is kind of a which is kind of a word by word formulation of the previous statement, previous definition. Is it clear? Any doubt in this one? Okay, I hope it is clear. And basically, this is going to give us the definition of cat-zero spaces. And we will generalize this thing in a more general setting for any positive. Okay, so for any real number kappa, okay, that will be known as the cat-k condition. Okay, so let me just mention. Let us say we have this geodesic triangle A, B, and C, and we have another comparison triangle which is A dash, B dash, and C dash. What we're going to have is like we take any point U and we take any point V, okay, and then we have some point U dash, and this is nothing but some point V dash, and we have a comparison map from this triangle is known as T, and we'll say this comparison triangle as T dash, and we have map from so this T dash to T dash, so that f of A is equals to A dash, f of B is equals to B dash, f of C is equals to C dash, and f restricted to any side is isometry. Okay, so we say T satisfies that zero condition if for every u comma v belonging to T, this distance, basically the inverse image of f inverse is basically one Lipschitz. So what we mean by is like the distance between u comma v is nothing but less than equals to d Euclidean of u dash comma, where u dash is basically fu and v dash is basically, okay. In other words, this is like f inverse is one Lipschitz. Okay, so this is the cat zero definition is nothing but it is just the comparing the geodesic triangle in the metric space which we are talking about to the geodesic to the triangle in the Euclidean space. Okay, and once that comparison satisfies this condition, we say that the metric space satisfies the cat zero condition. Okay, so here our in this case our model space is Euclidean space, okay, which means that it has a curvature 0. To define the general cat k spaces, just underline this one. So to define the general cat k spaces, we need the model space for constant curvature of any k for any real number k. Okay, so for that one we need the we need the three model spaces. to define the in general cat case spaces. Okay. By the way, up to this, everything is clear? Hello?
Yeah.
Okay. So, by the way, yeah, this is a good exercise. It would be good exercise to do this one. Geometrically, just try to see that the cat zero condition is nothing but the definition 2 and this is definition 1. Compare the this is fairly easy, but it would be nice to just see the geometrically how this is going on. So say this is definition 3. Okay, compare the definitions. Okay, so now we are going to talk about the model spaces. The model spaces. So if k is equals to 0, we are going to define it as m0, let us say m0n, space of constant curvature constant curvature 0, which is nothing which is nothing but Euclidean space Rn with the Euclidean metric and the Euclidean norm. The next model space is if k is less than 0, we denote mkn as a space of constant curvature k. So this is basically this we are getting by dilating this upper half space by, so upper half is space with the hyperbolic metric. Okay, so that is the constant curvature -1, and what we are going to do is we are going to multiply the distance, means hyperbolic distance, by the factor by a factor 1 upon root over minus k. Okay, so once you dilate hn by this factor, this hn will become constant curvature metric space of constant curvature. Sorry, wait a minute. So this will become metric space of constant curvature k, where k is less than 0. Okay, if k is positive, our model space n will be of, this is positive curvature, n is positive curvature k, by taking, any idea what we're going to do this one? So what we're going to do here, so for constant curvature 0, like 0 we have taken Rn. For negative curvature we have taken this upper half plane, or let us say upper half space, by dilating it the factor 1 by root over minus k, so that it will be constant curvature k. What we're going to do with the positive curvature, means what will be our model space? Any idea?
Here,
Sorry.
air of radius.
Yeah. So we are going to just take the, by taking the sphere. This is the sphere of radius 1 by root k. Okay, and hence with the distance function, means the spherical distance function, this will be the This will be the constant curvature K positive. Okay, so now we have this comparison triangle, and the way we did in the cat zero space. So see, I was motivated to define the cat zero space. I was motivated by this definition of this triangle condition. Okay, so the way we have defined the cat zero space, in the similar way we are going to define the cat K spaces. See, for cat zero spaces, we are taking K equals to 0. So we are taking the comparison triangle in the Euclidean space. Okay. And once we take K is less than 0, we will take the comparison triangle in the upper half space, that negatively curved space with respect to the hyperbolic metric. So basically, we are mainly going to focus on the case when K is less than 0. So basically, our focus will focus on basically we will K is less than 0. Sorry, K is less than equals to 0, and the case K is greater than 0, which we are basically omitting, is broadly similar. Although there are some differences due to the fact that positively curved spaces such as spheres tend to be of finite diameter. Okay, but they are kind of almost the same. I will mention I will mention the reference where one can go through and see these for K positive. But in this talk, we are going to focus on for cat K spaces when K is less than equals to 0, means when it is non-positively curved. Okay, so let here will be our definition. This will be cat K spaces. Okay, so let X comma D be yes. Anything? Any question? Okay, I heard something. Okay, so let X comma D be a geodesic metric space. Okay. Uh, and we are going to talk about so basically intuitively what we are doing is, it is like say if I say that a space X with curvature at most K, where K is, let us say, less than equals to 0, what do I mean? I mean that this have a geodesics that move apart at least as fast as the corresponding ones in a simple model space of constant curvature K. Okay, that is what I mean by the Lipschitz, this Lipschitz thing. Okay, so here what happening is we have a geodesics that move apart at least as fast as the corresponding ones. So corresponding ones are in this case are in the Euclidean setting. Okay, of constant curvature 0. Okay, so this is our intuitive way to define the curvature. Let me just write it down. Okay. At K spaces. So intuitively, a space X with curvature at most K should have geodesics that move apart. Okay, so they move apart at least as fast as the corresponding ones in a simple model space. model space, let's say M of constant curvature K. So this is the kind of the whole idea, intuitive idea. Okay, so so to define K spaces for K less than equals to 0, we take, so let T be a geodesic triangle with vertices, let us say x comma y comma z in x. Okay, so this is a geodesic triangle with segments, a geodesic triangle with sides. Let us say this is x y y z and zx. Okay, so these are the sides. So let's say this is x, y, and z. What we're going to do is same thing. We pick a comparison triangle T dash with vertices a dash, let's say x dash, y dash, and z dash in mk. Okay, in mk, so that distance between x comma y is basically distance between. So in mk, let us say we have this distance dk, which is a to b dash, and similarly for other sides. So as I said, such a triangle always exists when k is less than equals to 0. That comes from the Alexandrov's lemma. So so it means that, okay, so here is our comparison triangle in the model space, which is, let us say, x dash, y dash, and z dash. Okay, again what we are going to do is take 2 points, u and v. Okay, and take the image u dash and v dash. Okay, now here comes the definition. So it is, we say that this will be the same the way we have defined the cat zero spaces. We say that T satisfies the cat K condition if the following inequality holds. What is this? So this is basically d of u comma v is less than equals to dk of u dash v dash. Okay, where u dash is basically f of u, v dash is basically f of v. So we are basically considering the triangles, comparing the triangles. We are basically comparing the triangles, and the space x comma d is set to be, the space is cat k space if uh, if every geodesic triangle satisfies cat K condition. Every geodesic triangle satisfies cat K condition. Okay, so I hope at least geometrically the idea is clear. We will see the examples later, but I hope what we are what is going on with these spaces, at least the geometrically like the geometric idea is clear. Any doubt up to this point? Okay, so we'll move ahead. And here comes our definition of non-positively curved spaces, or write it down here. So geodesic metric space x comma d x comma d has curvature less than or equals to k, okay, if it is locally cat k. Okay. It means that for every point x belongs to x, there exists a neighborhood such that the neighborhood equipped with the subspace metric is cat k. Okay. In particular, so obviously we are talking about k is less than equals to 0. So in particular x is said to be non-positively curved if it is of curvature if it has curvature sorry if it has if 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 it has curvature less than or equals to c. So I hope it is clear. So a geodesic metric space is said to have curvature less than or equals to k if it is like locally cat k space, and in particular x is said to be non-positively curved if it has curvature less than or equals to 0. So curvature, it means that it satisfies the cat 0 inequality or cat k inequality. Is it clear up to this point? Okay, so here are some examples. I'm going to take it as an exercise. Examples. This will fall under a more general theorem. So Hn is cat minus 1, obviously cat 0. Rn, the Euclidean space, is cat 0 and cat minus 1, but obviously not cat. Sorry. This would be cat 1, obviously not cat minus 1. These are fairly easy to see because see, this Hn is basically this has basically curvature minus 1, so fall under that thing. And the main theorem and one more theorem is this is a theorem which will again give an example. So I will consider this as an example only. So theorem, let us say A. Suppose k is less than 0, metric space is cat K if and only if it is cat J for all K less than J. Okay, so if we have a cat K space, it means that it will be cat, sorry, if we have a cat K space, it means that it will be cat J space for every J greater than K. Okay, and in the example section again, we have this another theorem. This is quite important. So kind of the idea of the proof of this theorem we will see in the extra session on the Riemannian manifold as a metric space. So this is, let X be a complete Riemannian manifold. And let us this K is less than equals to 0. Okay. So the theorem is X has curvature less than or equals to K. Okay. So this is in the sense of Alexandrov, means the cat zero geometry, in the sense of Alexandrov, if and only if it has sectional curvature. So sectional curvature means a sectional curvature of all tangent plane in that Riemannian manifold X. So sectional curvature sectional curvature, if it has sectional curvature at most K. Moreover, so see, there is a thing of local cat K and global cat K. Okay, we are defining the notion of cat K spaces, and then we are defining the notion of curvature as local cat K space. So here we are kind of defining two different things: cat K spaces and local cat K spaces. So at this stage, I'm going to mention that point. So moreover, X is cat K. Okay? X is cat K if and only if sectional sectional curvature of X is less than or equals to K, and basically the first fundamental proof of X is 0, that is X is simply connected. Okay, so that is the difference. Means complete Riemannian manifold is cat K if and only if the sectional curvature is less than or equals to K, plus it is simply connected. Okay, so it means that in particular, uh, basically we see that every Hadamard manifold is like a covering space of complete simply connected Riemannian manifold. Means it can be written as the quotient of Hadamard manifold and a group of transformation acting properly discontinuously and freely on that Hadamard manifold. So that Hadamard manifold is always a cat zero space. Okay, so let me just mention this thing. Definition is simply connected Riemannian manifold of non-positive sectional curvature. Non-positive sectional curvature is called Hadamard manifold. And by this one, it means that every Hadamard manifold is cat zero spaces. So every in fact, it means that a Riemannian manifold is a Hadamard manifold if and only if it is cat zero. So every Hadamard manifold is cat zero. And so it means that every simply connected planar domain, every simply connected planar domain with 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 the hyperbolic metric, or one can say the Poincaré metric. The hyperbolic metric is cat zero. Okay. See, the hyperbolic metric is nothing but the Riemannian metric, and we can apply this theorem. Okay. Here I want to mention two more important examples, which is kind of a topic of current research, is related to the cat zero geometry of the. Okay, by the way, I haven't mentioned what I mean by. Wait a minute. So, cat k just okay. So this cat k thing comes from the Gromov. Okay, in the honor of Gromov, the of Carton, Carton, and Alexandro, Propongo. Yeah, so I wanted to mention two more things. So this will come under example only. Examples. So this is theorem B. Again, example will be theorem C, which will be like. Remember, I have mentioned about the quasi-hyperbolic metric. See, the quasi-hyperbolic metric is not in general Riemannian metric. Okay, so we can't apply this theorem B on the quasi-hyperbolic metric, and also not on the Kobayashi metric in higher dimension for domains in CN. We can't apply this thing because they are not comes into the framework of a Riemannian metric. So theorem C says that this is a recent research work. It says that every simply connected domain in C is cat zero with respect to the quasi-hyperbolic. The quasi-hyperbolic. This is a recent result by David Heron. I kind of forgot one. Yes.
So quasi-hyperbolic mean the rho function is distance between x comma delta omega.
It is 1 upon the distance.
One upon okay.
So that is not Riemannian because that is not differentiable inside the domain. So,
yes.
And the other thing, I kind of forgot this one. There's a recent work on the. I will mention this when I will upload the notes. Is regarding the take a domain. Just take a Kobayashi hyperbolic domain. This is hyperbolic domain. So this work is related to the to find the necessary condition for omega comma k omega to be cat zero. Okay, so it is and the necessary condition is something related to the convexity of the domain. necessary.
Oh, this will be M convex. I have seen his result later.
Yeah. Okay. Yeah. So it will be M convex or something like that. Yeah. So necessary, but I don't know whether that result is. I mean, I haven't seen
Published.
that paper.
Yeah.
I
Yeah,
haven't
I
read
have
that
not
paper. But yeah, that result is there. Necessary condition.
Yeah.
Necessary condition for omega comma k omega cat 0. Obviously, see, okay, I haven't mentioned this thing because that will be out of scope for this short course. That is kind
What
of.
about
Yeah.
what about the higher dimension version of the above result in
Quasi-hyperbolic?
yes.
Yeah, it is not like characterization is not known yet. I mean, one can easily construct the examples of higher dimension simply connected domains in Rn, which is not cat 0 with respect to the quasi-hyperbolic metric. It's just that
No,
you have to.
no. I'm asking that. Oh yeah.
That's what
What
you're
if
asking, huh?
about C about the theorem C.
Yeah, about the theorem C means you have to take the simply connected domains in Rn for n greater than equals to 3, equip it with the quasi-hyperbolic metric, and check whether it
Okay.
is cat 0 or not.
That's
Isn't it?
not always true, right?
Yeah, that's not
You say
always true.
that.
I mean, one can construct some easy examples.
Okay.
But yeah, the necessary and sufficient condition is also not yet known.
So in your simply connected domain in C, it is not equal to C, I think.
Sorry. Yeah. Oh, sorry. I mean, it is not equals to C because then we can't define the quasi-hyperbolic metric. We don't have any boundary point. If you just take the C.
Fine, but then it is biholomorphic to ball.
Which one?
But then it is biholomorphic to ball.
Yes. Yes. Then.
Okay.
But
Then,
as I said earlier, that quasi-hyperbolic metric is not Riemannian.
Oh, that's why. Oh, yeah. That's excellent.
Yeah. So I mean, in both the cases, in quasi-hyperbolic metric and the Kobayashi metric, the necessary and sufficient condition is not known yet. One
So
thing
I
is
think
that,
a simply connected thing. I think if a domain in Rn, so if a domain in Cn is C convex, C convex means intersection of a line with the domain is simply connected.
Yeah, I understood.
Then it's cat 0 with respect to the quasi-hyperbolic distance or not. It's a bounded C convex domain. For is it known? Bounded C convex domains are have uniform squeezing property.
I mean, I don't really know, but I think we see if a space is cat 0, it has to have a unique geodesic between any 2 points.
Unique?
So means unique geodesic. It has to have a unique geodesic between any 2 points.
That's
like if you
two
see
in
any
C.
simply connected, so any simply connected domain in C with respect to the hyperbolic metric that has a unique geodesic between any 2 points.
So can you please give the proper more about the difference of theorem C where I can get that result? I can't see that.
Okay, yeah. Once I upload this lecture note, I will mention the proper reference. Like.
Okay, thank you.
Yeah, that I will mention.
Oh.
Okay, so I will stop here, and next day we will talk about the Gromov hyperbolicity and the comparison between all these things. Yeah. So, any other question?